Numbers are a concept that we take for granted, first and foremost. We use numbers in our everyday life all the time. We hardly ever actually stop to think about, like, what are they, like, what really is a number, and what sort of properties does our number system have that we take for granted, so on and so forth. So, what really is a number? It's really just a concept to talk about quantities of things. So here inside of this circle, I have some number of dots right here. And over here, I have defined a set called A, which contains 4 elements in here. Well, contains some number of elements, A, B, C, and D. And so we can define a number to just be something that quantifies how many things are in a set. So the number that we assign to this set right here, the number like associated to the set A, in our numeration system, in our base 10 number system, we would write this symbol on here and we would call that 4. Right, and so we would say like the same thing for like whatever this set over here is. These are different looking sets, but they both have in our minds the same number of things in there. Right, there is like some sort of correspondence like to each of the elements over here. I can like set up a correspondence between like the dots over here and the letters over here. So to us, these two things would have the same number of elements in here, and so they would describe the same number. Well, how do we say that two numbers are, or one number is bigger than the other? So here's an example. I have same set A is up here, so this has 4 things in it. It has A, B, C, and D in there. And I have the set B, which has a smaller number of things in there. It has A, B, and C in there. So right away, you can tell that this is going to be giving us a smaller number than this, but why? So one thing that we can say is that B is a subset of A because each element in B is also in A. Right? This element A also shows up in this set. This element shows up in that set, and this element shows up in that set. You could not say the other way around. You could not say that A is a subset of B. A is not a subset of B because D does not show up anywhere inside of the set B. So we would say that the number associated to B is less than or equal to the number associated to A. And because this is a proper subset, there are 2 symbols that people use for proper subset. There's this one right here, which is kind of like a strict less than symbol. Some people do that. Some people don't like that. They do this, where it's kind of like the same thing that you do for like a not equal sign. They put like a slash through it. Either of those are fine. We're not going to really worry about the distinction in this class. But anyway, so you could say that B is a proper subset of A because there is something in A that does not show up in B. And so we could say that the number associated to B is strictly less than the number associated to A. Okay. This gets slightly more nuanced if I have something like this. So this also has 3 elements, same as B. And so we can tell, well, there's going to be less things in here than in A. So this should give us a different or a smaller number than the number associated to A. But why is that true? So excuse me, I'm just going to get rid of this. So one way that you could say this is set up a correspondence between this set C and a set which is a subset of A. So set up a correspondence between C and some subset of A, and that'll tell you that this is going to be smaller than A. Or you could think of it like this: just go right away to set up a correspondence between elements in C and elements in A, and then see if there's anything that you missed right here. As far as like being mathematically rigorous, like the first thing, setting up a correspondence between C and a proper subset of A is probably the more mathematically rigorous one, but however you want to think about it, we're not going to worry too much about that. So a few properties of number systems that I want to talk about. So a number system can be additive. What does that mean? So the tally system over here is one example of an additive system. It is additive because so each tally just represents just the number 1, and to get the number which like this collection of symbols represents, you just add up the values for all of these tallies. So we have 1, 2, 3, 4, 5, 6, 7, 8 tallies over here, and so we add those values up, and for us 1 plus 1 plus 1, just do that 8 times and you get that number. The Egyptian system is another example of an additive system. So here, this guy right here represents 1 million. A fish represents 100,000. One of these like scrolls. The book calls them scrolls. I don't know why they are a scroll, but the book says that they're supposed to be a scroll. Represents 100, and then tallies represent 1 again. So this number right here represents 1,200,305. Right? And so we're adding up all of those values together. A system can be subtractive. The Roman numeral system is a great example of that. So in the Roman numeral system, you could have the symbol like IX. So I represents 1, X represents 10, L represents 50, V is 5, etc. If you put an I right before an X, what this now represents is, so it would not be like 1 plus 10, it would be 10 minus 1, because the 1 is like coming before that, right? So this is like subtractive. This represents 9. If I did XLVI, so the X is coming before the L, which means that instead of representing 10 plus 50, it's going to represent 50 minus 10. And then the V comes before the I, so these ones are going to be additive right here. So we are going to add 5 plus 1. So this number right here is 46. MCD, so M is 1,000, C is 100, and D is 500. So 1,000, 100, 500. So because the 100 becomes before the 500, this would represent 1,000 plus 400, or 1,400. The Roman numeral system is also multiplicative. Being multiplicative, I think, is pretty rare in a number system. We won't talk very much about it. You could just represent multiplication by like throwing in a symbol. In particular, they use like a bar. And what did the bar represent? It really just represented multiplying by 1,000. So XIX represents, so you have a 10, a 1, a 10. So this represents 19 over here. And if you put the bar over it, it's 19 times 1,000, or 19,000. One thing that this highlights is that order matters a lot in certain systems. So in some systems, it really does not matter at all. Like in the Egyptian system, if I wrote this collection of symbols like I did before, it didn't matter what order I wrote this collection of symbols in, because like each symbol has a very specific meaning regardless of where it appears in the number. Like this like man standing here like just represents a million, no matter whether it shows up here or whether it shows up here. You got two fish down here, 3 scrolls up here, 3 scrolls down here, same number of tallies, so they represent the same number. Whereas down here, if I mix up the order of these two numbers, or collections of symbols rather, they're going to represent different numbers. This is going to represent 19, whereas this is going to represent 21.